So yeah, in the morning we presented the measurement system SCORP and the analysis tools Cube and Scalaska. So and we just yeah hit only the easy part. So we just used SCORP as a preposition for the compiler. So instead of using FTN, we used SCORP FTN. This doesn't work. Well, okay, here we are. So I mentioned earlier that this doesn't work for auto tools or CMake based build systems. So here we have basically a two-way step for building. So first we have some kind of configure step or CMake step, and then we have the make step. And we need to make sure that during the configure step, SCORP isn't active, because during the configure step, sometimes the compiler is called, and if SCORP is already involved in this step, the output or SCORP will generate some output, so some experiment directories, and also the output might be parsed by the configure system and might produce wrong results. So this basically means that just prepending the compiler with SCORP doesn't work. So therefore we created some wrapper scripts for the compiler. So here, for example, for the ICC compiler, we have a SCORP ICC, or for the C++ compiler, we have a SCORP ICPC that can be used instead of, or this can be used as a replacement for your real compiler. So it's not SCORP blank ICC that you would use in a very simple build setup, but it's just you replace the ICC with SCORP-ICC, like is done here in this CMake example. So you have a CMake here, CMake call, and you specify the compilers for your code, and instead of specifying the ICC, you use the SCORP-ICC. And in addition, you need to switch SCORP off during this CMake call. So, and you do this just by adding this environment variable here, SCORP wrapper equals off, and then you can run your CMake or your configure script without any problems. So the magic here is then that SCORP-ICC just calls the ICC underneath and does nothing SCORP related. So then you end up with some make files, and when you type make, the SCORP-ICC is invoked and does the usual stuff. So it does the instrumentation of function enter, function exit during link time. The MPI or the SCORP MPI libraries are linked, and all these other library interposition magic takes place. So if you have a CMake or AutoTools-based build system, keep this in mind, because with the approach we showed in the morning, there will be no success. So there's some more documentation here. If you call this command SCORP-wrapper-help, there you find also some environment variables that can be used to pass, for example, the --user flag we used in the morning to SCORP, and also to pass some additional variables to the compiler. So, okay. Then C++ applications sometimes create lots of overhead. This depends on the compiler. So, for example, the Intel compiler automatically instruments all the inline functions. So if you have a lot of inline functions for example, from the STL, or for some other from other libraries like Boost, you get an instrumented executable that creates a huge amount of overhead. But as I said, this depends on the compiler. So, for example, for GCC, we will not instrument the inline functions, and newer compilers based on Clang will also will not instrument the inline functions. So lots of new compilers or newer compilers are based on Clang. So for example, the newer XL, the Fujitsu compiler, and also upcoming PGI compilers are based on Clang. And there you won't see this huge overhead for C++. But if you see it, you can switch to sampling. So sampling at the moment works only for x86 systems. And we need to find a libunwind library when configuring SCORP. And this can then basically be used instead of the compiler based instrumentation, and you should then also pass the -- no compiler option to SCORP, so to further reduce the overhead. So, and then, as just for an example here, we see a Vampire measurement here. So the timelines here above this is with compiler-based instrumentation, and here is with sampling. So you just see, so it's the same program, but it's a less disturbed measurement. So and this here is basically the overhead from the instrumentation that could be reduced by switching from compiler-based instrumentation to sampling. Okay, next topic. This is wrapping libraries. So lots of applications use third-party libraries. So for example, FFDW or MKL or some other libraries. And with the default SCORP way of instrumenting and measuring stuff, you won't see any calls to these libraries unless the libraries are also instrumented with SCORP. So usually you are not the developer of the third-party library, and you might not be interested about the internals of the library, but you want to actually want to know how many time you spend in this library. And therefore, we developed a mechanism to instrument the API calls of the libraries. So therefore, we need a C header or C++ header file. And then we have basically two steps. So the first steps here are done only once. So we need to wrap this library. This is a multi-step process here, which usually is done by some system administrator. And then once this wrapper is instrumented, it can be used quite often by every user of the SCORP installation. So for building a wrapper, we just need a header file and a simple example application. And with this header and the example application, we parse everything that is in the header file, and we generate wrappers for these functions. So these functions then can only be filtered, also be filtered with the filter mechanism we used also for SCORP. And then the wrappers need to be built and to installed. So here is basically short overview of the commands. So first you init the library, you give it a name, here ffdw, installation prefix, language, and here come some flags that are needed to build the example program. So you need to provide the include directory of the library and some other flags, and also you need to actually link the library. And this will create several files in this working directory. You go into this working directory, find some README document that you should carefully read to get some information on how to build and configure this wrapper. And then you just do some make check, install check, and then you can use the wrapper. To use the wrapper, so I need to go back a slide here. You pass this dash libwrap equals score P when you instrument your application. So this needs to be done, during instrumentation, and then you can use this wrapper. And here's an example. So it's again a vampire display here, and here we see the time spent in FFTW. It got a special color here, and we see that FFTW was used here in these on the master thread of each of these ranks in the beginning of the program. Okay, next topic is memory usage. So this is already in your instrumented executable. If you use the default instrumentation, and we can determine the maximum heap usage per process, we can find some frequent small allocation patterns, and very important, we can also find some memory leaks. So this works for C and C++, for MPI and SHMEM. For Fortran, it's only works for the GNU compilers. This is due to the fact that we use library wrapping for catching the malloc and realloc and all the other calls. And Fortran compilers, different from the GNU compiler, have their own mechanism that we don't intercept. And here again, we see some score P environment variables, so which need to be specified to switch on the memory recording. So it's just score P memory recording equals true. And if you want to do this for MPI, so then you have the second variable here, and then like before, you just run your executable and get some more metrics here. So for example, here the maximum heap memory allocated. We see here that the different ranks uses different amount of maximum heap memory. And here we see we have the metric selected bytes leaked. And we then see here in the call tree the allocation calls that weren't paired with the call to free. And this then gives you a hint where to look for to fix your program. Okay, then if you have an application using GPUs or NVIDIA GPUs at the moment, so you can record data from the kernels. So we have a score P CUDA enable variable here that is document, or the options you can give here are documented in the documentation. You need to look it up there, and we'll then get some information about the CUDA stuff. A similar environment variable is for OpenCL. So here we can record something about the API and the kernels. For OpenACC, yeah, it's again an environment variable, as the configuration is always done using environment variables. And for OpenACC, it can be combined with CUDA. So or usually you use OpenACC on a or execute OpenACC on an NVIDIA device, and then so OpenACC then translates to to some native CUDA calls. And this then looks like.
Sorry, you maybe didn't see it. Sorry.
Yeah, David.
Can you see the chat? Maybe you can't see the chat with your.
Okay.
No, I can. Is it possible to aggregate that heap memory allocation per node? Because in practice, that's often your constraint. You know that it's the within a node when one rank could do a lot of memory and other ones maybe not much, but it's the total per node that is the physical constraint.
Total per node. Yes, of course. If you collapse,
Sorry,
here.
Perfect.
Yeah, so it's the same mechanism in Cube. So if you collapse the node VMO here, then you see the memory, so the aggregation of the memory that was used per node.
Fine, yeah. Excellent, thanks.
Yeah. Okay, so here is an example of an application using GPUs. So here we have the timeline here, the master thread. And here we have an additional CUDA timeline or device timeline. And here these black lines here, these are host device memory transfers. And so the blue boxes here are some device activities. So this here is an example where we use OpenACC that then, which is here the pink color, and this then translates to the blue CUDA kernels here. So we are kind of limited what we see with GPU devices by the libraries we need to use. So CUDA comes with the kubectl library, and that's the library we use for getting some data from GPUs. Okay. So then Brian already mentioned performance counters. So we can use performance counters from different sources. So very well-known source is PAPI. So there's a library developed by University of Tennessee, and we fully support this again with some environment variables, metric PAPI, and here you have a comma-separated list of counters. So depending on your system, there are different counters available. So you can see this using the PAPI avail or PAPI native avail command, and you then put the desired counts here as a comma-separated list. So you need to be aware that you can't that some of the counters can't be measured together. So, but this is you need to look this up in the PAPI PAPI documentation. There's also a metric PAPI, and then here per process. So this is special that only for the master thread of a process we collect this data. So with the default one, we collect data for every thread. Another source for metrics are the perf counters. So it's basically just a different name for the Scorpy metric environment variable, and you get a list of all possible variables using the perf list command. You can also write your own metric plugins. So there is a repository here at this address where you can find some examples. It's basically it's quite easy to write your own source for metrics that you can then also see in Cube and like you see the PAPI counters there. Yeah, okay. Then we have an API to for you to add some macros in your source code. So, for example, if you want to have some coarse-grained phases for like in initialization, solver 1, solver 2, and some finalization, you can put some macros in there. And if you use conditional compilation, you can basically leave them in your source code and on a regular basis, for example, do some performance regression testing, which is very coarse-grained. So this might be something to consider. You can also subdivide some functions. So if you have huge functions with several loops inside, then you can divide this function into several areas. And for all of these subdivisions, you then also can get some hardware counter measurements. It's just like a region, like function enter, function exit, for use in this compiler-based instrumentation. To activate this user API, you need to pass the --user flag to Scorpy as we did in our BT example in the morning. So this works for Fortran CC++, which we see here. So here we have Fortran example. So for each region you use, you have basically 3 calls. So first you have a Scorpy region define call where you pass a variable name, and then you have the begin of the region and the end of the region. Basically here are events created in the measurement core. You need to pass the, the variable, some name that will then appear in the cube display, and some special region type. So this is, and in case of Fortran, you might need to change the file extension so that the compiler detects that this file needs to be pre-processed. Yeah, I forgot to say you need to include the Scorpy file that defines these macros here. Okay, same example just for C. So you have the define, you have the begin, you have the end, and everything else it's basically the same. For C++, there is some convenience here. So we have just one macro, so Scorpy user region. And if we put this here into an extra block, so then here a variable is created, and a name needs to be given, and the region begin call is made here. And if we leave this block, because this here is will create a local object, the destructor of the local object is called here and will be responsible for triggering the region end call. So this for C++, this might be more convenient. So in addition, you can switch recording off and on again. So for example, if you're not interested in, let's say, the initialization phase, you can just put a Scorpy recording off before some code, and then later on you can do a SCORP recording on again. You need to make sure that you don't mess up the usual nesting of region enter and exits. So this needs to be preserved, otherwise you get an error message. Yeah, this here was the Fortran case, and for C, C++, it's basically the same. Okay, that's it for some further features of SCORP. So SCORP, as already said, is community-based code developed by several partners for instrumentation and measurement. With an instrumented executable, you can you can create call path profiles or event traces, and also some online access measurements. It's available under a 3-clause BSD license, so it's open source. You can use it, you can modify it, you can even contribute back. That would be we quite often, or not quite often, we from time to time get some patches from experienced users. So this is really nice for us. You can find more information here on this scorpi.org website. If you have an installation, you find the documentation under the installation prefix in PDF or HTML format. But you can also find the current, the up-to-date documentation here under this website. If there is a problem, if you need help, please send a mail to Scorpi, to support@scorpi.org. There's also a newsletter that you can subscribe, which has very low which is a very low volume mailing list. So, well, let's see. Okay, so here is the mailing, the Scorpi website. It's also hosted by the on the VI-HPS site here, where also the tuning workshop information can be found. Here you can find the current releases, not only of Scorpi, but also of the libraries that we use. So there is an OTF2 library that can be installed separately. Also the Opari source-to-source instrumenter for OpenMP. And here's a link to the Cube libraries that are also needed by Scorpi. This can be found on the Scalaska website. There's also the possibility to download some development tarballs that are automatically generated by our CI system every time we have a commit to master. So here, for example, you see the latest master commits. We are working on OMPT and also on porting to the new Japanese supercomputer, the Fugaku system. And we are working on supporting the AMD optimizing compiler. This is only a few things we are working on, because not all of the features are working on are part of the CI system yet. So we test our features on several platforms. So here's just a small example of the pipelines we run for every commit to master. So we have, for example, here a PRACE system. Then we have some Docker containers with different configurations. We have this Fugaku system here, which failed at the moment. Some systems in Jülich, Strahd system in in Germany, and we are at the moment also working on getting the Marconi Power 9 system under CI coverage. Yeah, so basically that's it for the additional features of SCORP. And if you have any questions, please let me know. And does anyone have tried to follow the exercises from the morning, or try to build the BT example, or maybe your own code with SCORP? So if there's any problem, or if you can provide some support, please let Brian and me know about this.
So, Christian, apologies, I couldn't attend this morning's session, so apologies if this is a stupid question, but is all the software installed on Archer centrally, or have you had to put updated versions into for this course?
So we have modules here. Let's see if we'll find it here in
I was
this.
planning to have a go on one of my own codes, but I just didn't want to go down the. If they're centrally installed, it's fine. I can find them. I just wondered.
Yeah, you need to use this module setup here. Yeah.
Fine. Okay.
They're not part of the default set of modules at this point, at least not the latest versions.
Right. So, but that's okay. So it's not specific. It's not specific to this course, but it's slightly different from the. That's fine. Okay.
That's where all of the older versions are installed as well, but the modules just haven't made their way into the public set.
Okay. Home Y07 classical modules. You mentioned that there were some restrictions to do with the memory profiling due to having to intercept malloc and that not being possible. Sorry, restrictions for Fortran. Is that the only
so
place
it works for GCC, but it doesn't work for other compilers.
In general, functionality is
so we do some. So we at the link time we intercept the calls to malloc, calloc, realloc, free, and maybe some more. And if the Fortran compiler calls these functions, we can see the events. If Fortran does some own memory management, so we don't intercept this because we don't know the details of the mechanism.
But outside of the memory management, the functionality is generally common across C and Fortran, isn't it?
Yeah.
Yeah, fine. Okay. I had one final question. Sorry, again, you may have explained this morning, but you showed a Vampire timeline. Was that the Vampire tool using? That was just using the Vampire visualizer, was it? But reading one of is that?
Yes. So the let's see. So for Vampire, you need to do trace measurement. Yeah.
Right.
So so here, for example, you need to do a trace measurement, and then you generate OTF2 output files that can be used either with Scalaska, so to do some further automatic analysis, or you can just view the timelines and do also some other sophisticated analysis using the Vampire tool.
So all the tracing is done open source, but if you have that, if you've bought a license for Vampire, you can do different analyses with that tool.
Yeah. Well, doing the measurement is open source. Also, the OTF2 library is open source, but the Vampire tool is not. So you need to obtain a license. Yeah. So at the moment, I don't know of any open source tool that has the capabilities of OTF2. So
I mean, sorry, how to use Vampire
on Vampire? Sorry.
I haven't used Vampire for a few years because we had a license on our old system, but not on the new system. But is it under active development, Vampire?
Yes. Yes. Mm-hmm.
Okay,
yeah,
fine.
so Vampire is developed at the Technical University of Dresden. They are also actively contributing to SCORP. Yeah, so this is their product. So like Scalaska is a product in Jülich. So and we both together developed the measurement system that is needed for both of the analysis tools.
Because what I look, so Vampire has very, very sophisticated functionality, but even the ability to do a simple sort of message plot would be useful. And you should be able to write your own tools on top of the open trace format, shouldn't you? That should be something which is doable, I guess.
Yeah, this is doable. But with if you do tracing, usually you have a create huge amount, or you have to deal with a huge amount of data, and so scalability then becomes an issue. So there is a so the Cube developer tried to or he has a plugin to Cube that can read and display small traces. So, but this is just a toy project, so not intended to replace Vampire, but it is possible. It's not so difficult if you know or if you dig into the OTF2 format. So it's well described, and you can create your own viewer or own analysis tools if you have the resources. Yes.
Right. And which again, apologies if you meant which at what level is the sort of time skew between the processes dealt with? Which product ensures you have a common timestamp? Is that does OTF have that in it, or I don't know? I've never quite.
So during the measurement, we do some timestamp interpolation, and we pass this information to OTF2, and then on the analysis side, you just use this offsets between the different processes. Yeah.
That's stored in the OTF file. Is it?
That's stored in the OTF file, and so Scalaska also comes with the with a tool to synchronize clocks. So it goes through the entire trace and looks for some inconsistencies between processes, and then somehow modifies timestamps a little bit so that the inconsistencies are fixed.
Okay. Fine.
And you can this generate or this modified trace and also use it with Vampire then.
Okay. So I'm just looking at this schedule. Do you plan to be available now till the you changed the timescale slightly from the we're back on the, aren't we? That would have been the next start at 2 and the next break would be 3:30. No, I'm wrong now. I can't make it.
No, the next break's at 3:30.
Yeah, we still have 3/4 of an hour approximately.
Sorry, I had a cached version of the timetable. I just reloaded it. That's why it was wrong. Sorry, I understand now. I had an old version of the timetable in my cache. I understand. Okay. So is the idea that you'll be online to help people if they have any issues is that your plan for the next till the final session?
Mm-hmm. Yeah,
okay.
I think so. I'm available. Brian, I think you are also.
I'm available, and I think Judith and Lau are also available if there are people using the tools from yesterday.
I want to try and get Scholastica going on my test program, but I may be asking you stupid questions. I'll look at because I missed this morning, but give me a few seconds and I'll try and get up to speed.
People at least should be able to go through the exercises, which we did. We went through them quickly, but the steps are documented in the slides. And if there's any questions or any issues, then we can step in and help. And if you get past that, then please try the tools with your own codes as well. If you have a code that's building and running on Archer, then try out the tools as well.
Christian, sorry to bother you. I don't know if you're there.
Yeah.
I have to use the Intel compiler for, there's some issue with the I/O with Cray. You mentioned, is it a special wrapper for, I was looking at the documentation, but do I just do the same thing?
Yeah, usually you just so what kind of build system do you have? It's just a make file?
Yeah. Very simple make file. So
then you just prepend the compiler, so the C or capital CC or FTN with scorp.
Okay, fine.
That's it. So
you said at some point there were special wrappers for Intel. Maybe that was different.
So I mentioned the Intel compiler as they are special with regards to the overhead they generate for C++ codes.
Oh,
so
that's right.
They instrument all the inline functions and are therefore a little bit special.
That's a C++ specific thing.
Yeah.
Okay, right. Thanks. I'll be thanks.
David, before you have to make sure you have the Intel programming environment loaded before you load Scholastica or before you load Scorpion.
Yeah, luckily I had that. I was in there. I'd already done that. Yeah, I realized it. Yeah, I was lucky. I already had that done. That's fine.
Because if they mismatch, then all sorts of weird things can happen, which are usually not good.
Yeah, I guess you get the wrong library. Yeah, I know. I've seen that before. It just, you get all kinds of weirdness. Right. But I don't need to. Do I need to load the Scholastica module? Oh yeah, I do. Sorry, I'm being stupid. Fine, it's okay. No.
The Scholastica module automatically loads Scorp on the way it's set up on Archer.
I was asking. I'm running because I'm running my own script here. I wondered if I needed to load the module in the PBS script, but I just will. Sorry, I don't know. Fine.
It shouldn't hurt to load the module. Sometimes it's necessary, sometimes not. Depends if you're using dynamic linking, or if everything's static, it shouldn't be necessary.
Fine. Yeah, there's a problem. There's always this problem in Archer that the home file system isn't mounted on the compute nodes, but I actually it's saying, yeah, I'll see. I've put it on. See if you're working. Okay, cheers. I just get this weird error with binary I/O. It works with for very large files. Cray what's the new Fortran ILO type? File type equals stream, which is just raw data. Doesn't seem to work for big files. It does with the most recent GCC, but not the old ones. And the Cray seems stuck to a reasonably old GCC, so I can't. It's just a silly thing, but
The Scorp installation, which was done on Archer, was using the default for GCC and the default for Intel. So I know that you have newer modules, but I just built things with the default versions. Which
they're not that much newer, actually. They're not new enough. I had a look. It's best to use the default ones. I think it's just you can for serial code you can load for serial code you can load a more modern GCC, a very modern one, but the Cray programming environment overrides that, so you wouldn't have access to it within within the for parallel jobs, so it's fine. Hi, I think I'm being stupid here. I've compiled and run the job. It doesn't seem to produce any different output. Do I need to set any environment variables to get it to work?
No, so if you have an instrumented executable and you run it, then there should be an output directory which is called scorp dash and then a very long timestamp if you haven't set any environment variable. So are you sure you're using the instrumented executable?
Yeah.
Can you do an LDD on the executable? It should mention then, well, if it's not linked statically, it should mention some scorp libraries.
LDD. Okay, come on. Okay, LDD. Oh, that's weird. Oh no, it's static. Okay.
Then you can do an nm, your executable name, and then pipe grep or p. So there should be lots of scorp symbols.
Loads of scorps. Okay.
So if there are no scorp symbols, then something with the instrumentation went wrong.
But there's lots of them. I do nm minus e, and there's tons of them.
Yeah.
There's in fact more than 1,000. So. Yeah. Running it. Maybe it's a. Should I try with the GNU compiler? Maybe I do have some files I can read with the. Should that's very strange. Why don't I try
and
you
use the standard gray CC or capital CC or FTN compiler?
Yeah,
and it's an MPI application, or well, but this shouldn't matter. So we should get this automatically.
You see my screen?
Yeah.
So it's just it's this one I'm doing. Sorry, this one here. It's just a bit. I mean, it's just.
Yeah. This is used for compiling and for linking, or is there a special link step somewhere?
Oh, yes.
And then you need to use scorp for linking as well.
That's my problem. Sorry. Okay. Oh no, it's linking as well.
Yeah.
Let's just do. That looks correct.
That looks correct, yeah.
If I do sorry.
It's you did an LDD instead of an NM. So
yeah, there's lots there.
that looks like expected. So
Yeah.
if you run this, you can, yeah.
In the job, I'm just, okay. It's very simple, but I did that, and then I did an AP run with a few, and it ran. It didn't seem to produce any.
Can you add an environment variable in the job script? So yeah. Just do an export scorp underscore verbose equals true or 1. Yeah, it doesn't matter.
Okay. It's a couple of minutes to run. It's quite short, but the I/O in this program is terrible. I wrote it. It's terrible I/O. It takes forever. But it's just a little test program. But
as soon as it reaches MPI init, you should see the scorp directory produced.
yeah, I wasn't getting anything if in here. Oh, wait a second. Yes, I was CDing, wasn't I? Otherwise, it wouldn't have. Yes.
And what's in the output of the PBS files?
Just the in fact, it should. It'll only take a minute to finish now.
Yeah, but if it hasn't produced anything at the beginning, then it certainly won't by the end. But
oh, this will be live. Actually, I mean, it's actually creating the directory while it's running. Sorry. Okay. Yeah.
yes, I mean the MPI init is where it would create that directory.
Yeah. Okay. No, it didn't produce anything. If I look at this, I mean, I'll wait till we get this one just so you can actually see the one I'm running. How long has it been running for? It only takes a minute or so. Sorry about this. It's taking load. The I/O is slower than I thought.
When you enable the verbose output, you can get quite a lot of output when you're running with 500 processes.
Oh, I see. It's right. Okay. But at least that'll tell us it's being called.
Yeah, if there's no scorp output, then something is wrong. But
and there's a lot more.
You have the output. Yeah.
Okay, so it is.
Scorp is definitely in there.
So these are all 500 copies, I guess, of all the.
Yeah.
You're using the Fortran 90 MPI interface?
Yeah.
Oh yes, I am. Fortran 2008. Sorry, is that a problem?
Yeah.
Fine. Okay.
Yeah, this is a problem. Then we won't capture the MPI in it.
That's fine. Why is it? Is that because it's name mangled? Is it or something?
It's just that Fortran 2008 is using modules in a different setup for the MPI, which we're not able to intercept yet.
Fine. It's fine. I can switch. I had the MPIF 90. Okay, fine. That I should have thought about that. Fine. Okay. Why does that kill you? Is it name mangling that kill that, or is it something more sophisticated that means it doesn't work?
The interface is written in Fortran, and we're interpreting on the C interface.
Oh, so there's more done in the. I understand. Yeah. Okay. I see. It's actually a Fortran function now, isn't it? Rather than it being just a raw.
It's a Fortran module, and the whole setup is Fortran, which needs a different way of doing it. Christian, I'm surprised that we didn't get a warning at the end saying that there was no MPI in it. Normally there's a warning in that case.
Yes, you're right. Okay, I need to look into the code to see what. So we linked the MPI adapter, and we never saw MPI in it. Neither we saw MPI finalize, and we then could, when we shut down the measurement system, could issue a warning. Yeah, and then maybe also mention in the warning that MPI that the Fortran 08 wrapper are not supported yet. Okay, I will need to fix this. Yeah.
That warning used to be there, so it's do you think it was being removed?
Actually, I don't think so. Maybe this is a slightly different kind of situation. So I need to check this.
Sorry. No, I wrote this code quite recently, and I used it as a way of teaching myself the Fortran 2008 interface. But it's the 2008 interface is broken on so many systems that I had to do an option to do Fortran 90 because it's clearly not used a lot. The bugs you get clearly mean that a lot of people have never used it because even simple programs. Oh, there it is. Okay. Right, fine. We've got it now.
It's like all of these things. It's in the latest and greatest compilers, but it's not in enough of them or wide enough used that people are reluctant to rely on it, and it doesn't.
So much now. I mean, so many of the bugs missing out. So many of the classic Fortran bugs disappear with 2008 interface. It's really it's just the C interface. Sorry, it's just the C interface basically becomes the same, which is nice.
It has a lot of extra checking of the interface, which is nice. I agree.
Yeah, exactly. It does a lot. In fact, it catches a lot of. It checks. I'm a bit free and easy about passing scalars or arrays of length 1 and things like this, and it catches all that. It's quite strict, which is good. It picks up things like that. But your statuses are structures and things like that. It's all a bit nicer. Okay, fine. Now it's run. That's my output. Okay.
Now you probably want to get rid of the verbose.
Yeah.
And then now you saw that there is, I think there is verbose output that the MPI was initializes.
So how do I view? I want to view the sort of communications pattern. That's really what I was interested in. Well, it's probably. I need to install. Where's the slides? Okay, that's the next step. I need to get the next tool. Trace and answer with Scholastica. That's what I wanted to do. Do you recommend running Scholastica on Archer or doing it locally?
You should run Scholastica on Archer. So because it does a parallel trace analysis, or it can do a parallel trace analysis. You should use the cube. So the cube tool to display the results, you can use this locally.
Sorry, I was confusing.
The scan command that you put into your job script, that needs to be run on Archer.
Yeah. Okay, Scholastica analyze.
Yeah, but maybe you first do a Scopy score on the profile.cubex file. So for the PRACE experiment, you maybe need to filter out some region. Otherwise, the memory demands are too huge. So here it says it's pretty small. So yeah, so you see this Scopy total memory. So
Yeah.
it's just 127 megabytes. So this fits perfectly into the trace buffer. So without
But not the
any,
default. The default is only 16.
Oh yeah, Brian, you're right. So you need to specify this Scopy total memory in your job script as well before you do the trace experiment.
Fine. And you can run the analysis on any number of processes, can you? It doesn't have to be the same as it was run on initially, or is it the...
If you use the Scholastica analyze prefix to your AP run, then it will run as part of the same job, using the same compute nodes, the same processes.
But if I run it separately, do I need to use the same number of processes as I ran the application on?
Yes.
I do. Fine. Okay, fine. So I should do it in the same script. I can do it as a separate.
Yeah, it's much more convenient if you just do this scan-t for tracing. Then first we do the measurement, and we use the same resources for the analysis, and you don't need to specify this manually in a second job.
Yeah. Okay. We're running a bit late. I'll do this after that. I'll do this later on. Okay, but that's good. Thanks. I wouldn't have spotted that. I wouldn't have been able to debug the 2008 thing myself. So that's really useful. I wonder how much it the verboseness. I wonder how much overhead it puts in, but the verboseness probably puts in more. Actually, I'm still sharing, am I? I'll stop sharing. You don't want to see my window.
You're still sharing, but maybe you can do a cube on the. Can you run cube on that profile just so we can have a quick look at what it contains?
So I just run cube.
And then profile.cubex. This assumes that you have logged in with -x, SSH-x.
Probably. Take me one. Okay, so this is
by default it's selected visits at the top, but if you take the second metric down, it'll be time.
So say that again. Sorry.
If you take the second metric and the left-hand column, it's going to be the execution time rather than the number of visits.
Oh, okay. So
And then if you expand the middle or the right-hand column, we'll see how that time is distributed.
So I do. Sorry, being stupid here. Oh, I see it.
In the tree where the plus is there.
Yeah.
So main is pretty obvious for Fortran, and then below that, if you, the box is not showing the plus inside it, but you can expand it again.
Oh, okay, fine. Okay. So it should
So
all
now
be
that's
in.
your Fortran modules.
Well, this is actually a serial part. The parallel part is this is inclusive time, is it? Oh no.
It's inclusive when the node is closed. If you open the plus, then it changes to exclusive.
Okay. But PRSPMV is my big parallel sparse matrix vector. That's my big, and it's you
can see it in orange. There's another one above you in the previous tree. Yeah, and where it's orange there. That's the same function, isn't it?
Yeah.
So that one's expensive, but the other call later is not.
Oh yeah. Okay. So there's two versions of it, I think. Oh. Need to check that. Maybe it's not. But what is interesting is the this is communication. This gather tail OLAP. Oh no, it's okay. Sync is called. Sorry. Okay, I understand. I've overloaded this function. That's fine. I understand. But okay, that's interesting. That's really interesting. I've never seen that so clearly before. And it's doing it in point. I have a version which does it as a collective, but this is all point to point. So it's all I sent and I received. Oh, that's really
where most of the time is in the wait all.
Yeah. Well, this is very badly load balanced. This why I was interested is this is I have a version where I pre-process the matrix to make it so the matrix thing to make it better load balanced. And that's interesting actually. It's not surprising, but it's interesting to see it so clearly. I've kind of inferred all these things from global timings and scaling runs before. Do you see what I mean? I've never actually seen the times actually. What am I trying to say? Actually, and this is aggregated across all processes, I guess, is it?
Yes. So going to the right tree here, the one at the top that says ProgEnv Intel, and then you'll see a breakdown if you expand that per compute node and then per process.
Okay, I can maybe look at that. It was 20. It was about 500 because I think the load balance on this will be pretty shocking because it's a very naive load balancing of very high communication. But that is really okay. I hadn't realized.
But you need to select select from the middle panel something useful. Select the wait all, or select. At the moment, it's using one of the initialization functions. But if you select the wait all, you'll see how the wait all time varies, which is your measure of load balance.
That's actually reasonably well distributed, isn't it?
Look at the middle in the middle tab at the top. It says statistics. That's going to give you a better impression of how things vary. So it's varying from 24 for the slowest ones, the ones that take the longest in the wait all, 15 seconds for the fastest ones. So they're varying quite a bit.
Okay, bad. That is bad. Okay, fine. I have a version where I pre-processed the matrix with Parametis to get a better decomposition. The total runtime it reduced dramatically. It would be very interesting to confirm that it is in the places that I think it's in. Okay, so it's a long time since I used Glasgow. Sorry, it was probably a while back, and I'd forgotten it provided so much information on the first cut. My mind, you had to do a bit more work to get down to the. That's really nice.
By default, we actually include quite a lot. Sometimes it's way too much, and then you have to filter back and reduce it. And of course, you can add things as well.
That was really nice, actually. Okay, thanks. That's useful. So I could have SCP'd the file over and run cube locally if I'd wanted to, couldn't I?
Yes, I mean, it would be more interactive to install Cube on your workstation, on your laptop, whatever. But it's also handy to have, even if it's slow on Archer, just to do a quick look and see, oh, there's something there that's worth looking at in more detail. If you see it's completely wrong, then that's already a good.
I mean, so yes, Sam. Yeah, sorry. Yeah, I gave you moderator permission. You should have moderator permission. Yes, you are, because you're in the mod side. Fine. Maybe wait 5. It's not quite time. Wait a few minutes for people to come back, but
sure.
So actually, the X I don't know if it's quite a lightweight application, but that worked surprisingly well interactively from Archer. I mean, not.
Oh, the over X you were able to use it?
Yeah.
Paraprof? Okay, good. Good to hear that.
I am not that far from Archie. I'm only about 10 miles away. So,
Yes. Were you able to use the 3D visualizer on your?
I just did a very quick thing with Scholastic. I've not done much. I had to miss some of the lectures this morning, so I'm a bit behind. Sorry.
Okay, no problem.
But it's interesting to see how Collaborate works with people and so geographically dispersed, because we're going to be using it for teaching in the new semester when students will be all over the world. So there were concerns about people had concerns about the interactivity of, intercontinental, but it seems to be working. Okay.
Sounds good.
I've seen various people have had connections dropping and reconnecting, so
yes,
it's not always bad, but it's kind of up and down.
Collaborate's quite good at noticing those, but I don't. So you could call that a positive, but I don't know. I don't know if it's a heavier. I don't know if that's just people have problems with their connections anyway, or whether they're whether Collaborate's particularly. I know at the university level they're concerned for undergraduate teaching, because there they need to use more than 200 and odd connections, and that's a concern, scalability wise. But for us on our MSc, which is of order 50 maximum, it's hopefully not going to be a problem. I don't know if any of you guys have undergraduate or student teaching. I don't know what universities are planning worldwide. Samir, you're at the university, aren't you?
At the University of Oregon, they are planning to do it online to begin with, and most likely it will stay online in the fall. So
yeah,
that's the current plan.
We're
they
planning.
are saying that they may want to go to in-campus at some point, but I'm not sure how that's going to work out.
Yeah, we're planning online at the start, but then hoping to do on campus if it's available. But I suspect that won't be for us till after Christmas. I mean, with social distancing and such, like the numbers of students you can get in an lecture theatre is quite frighteningly small. So it starts to look complicated to arrange. I mean, you could broadcast live and webcast at the same time, of course, but that's in some sense more awkward than doing it live, doing it all webcast, because you have to juggle people in the room, and it's actually easier if you know everyone is online than having half and half, I think, anyway. But
yeah, you're right. It's
so
not
just
easy.
wait a few months. There's people coming back, then we can start.
Sure.
I do find Collaborate quite heavy on my laptop. It does. I do hear the fan whizzing quite a bit.
Oh, you know what? Let me. Is that better?
No. I'm saying what I'm saying is I can hear my. I'm saying my Collaborate is very heavy on my CPU, so I hear my cooling fan on my laptop going. I can tell.
Okay, I thought you were saying the fan that I had in the background.
No, sorry, I meant I can hear. I don't know if other people find that, but
okay.
I do find it quite heavy on resources. My old laptop would have struggled. Luckily, I brought my new one home.
So, but I experience the same with Big Blue Button, for example, or with Zoom. So my fan is always on if I'm in a meeting.
Yeah.
Yeah, a lot of such tools are rather heavy on the CPU, actually.
So yeah, Geert was having connection issues. Oh, so Geert's running Collaborate through Chrome. Okay, I have the. I'm doing it through Chrome as well. Okay, so yeah, I mean, I use Chrome because I find it more reliable than Firefox, but I get the feeling it's more heavyweight in Chrome than it is in Firefox. I might be talking rubbish, but I do. But the functionality in Firefox can be for a presenter can be slightly tweaky. What browser are you using, Samir?
Pardon?
What browser do you have?
What browser do I have? I'm using Safari on my Mac.
And that works with Collaborate.
Yeah,
Previously they said that it was not that it was problematic. Oh, that's good. That's good. As an attendee, anything works. It's when you're presenting it starts to get a bit more touchy. Just wait till one more minute and then. So I'm still recording. Okay, so we're going back. So Samira is going to carry on from yesterday, talking about using Tau to do performance analysis with examples. I think is that your plan? I'll pass over.
Yes, and we were looking. Let me share my screen just a sec, and share application. Okay, I assume you are able to see my screen now.
I can see it.
Okay, good. So we were yesterday we looked at how we can use Tau, and there were stages where we could start with a completely instrument everything test case for the NAS parallel benchmark, and then we created a selective instrumentation file. Then we applied that and then regenerated the instrumentation and created a more compact profile, which would then be useful for other tasks. So I'll continue with that, give a little overview, show some other examples, maybe even C++ examples with MPI, and the core here. The core way of doing the optimization of instrumentation was something like this. We first of all sourced our tau.bashrc. I hope you will be able to do that. If not, we'll just do that real quick today. Go to the NAS parallel benchmark directory. This should be already set for you when you source this. And then make suite with this. Go to the bin.tau, run this job, generate the data, and you'll see that initially it took about 24 seconds instead of about 20 seconds. I can launch this, go to paraprof, and then go create a selective instrumentation file, save it, transfer that file over, and then use the option such as this opt-tau select file equals select.tau. And then this has a exclude list. So instead of include, it has exclude. Then we export this, copy mind the quotes, it should be a single quote. Copy this in the BTMZ directory. Again, do a make clean, make suite, go to this directory, run it again, and then you'll see that the time goes down. And this is the more compact instrumented application. So just to do this, I have this in my path, and I'll just follow along with these steps. So I start with make clean. I tau make file. It should be in my path. I just did a make suite. MPI F77 equals tau F77.sh. This is using the compiler wrappers from Tau. I compile everything, and initially it has all the functions instrumented. It'll just take 20 seconds to run the code, so it's not too bad. And you can see that in the bin.tau, I remove any profile files I may have from before, and run.pbs. Is there a particular reservation I should use today, or maybe I'll just use the short queue?
No, there is a reservation. Sorry, I was muted. I'll just tell you what it is. It'll take me half a second to find it.
Just a second.
I put it in the.
Put it in the chat.
I'm trying to put it in the chat, but it's not.
Okay. There it is. $970, and then I can just say run.pbs, and let me just put this down. Watch stat -u $user. See when it starts.
Yes. Yeah, so, PBS does a linear trawl of the job file, and so sometimes it takes a minute or so to notice what job it is.
Okay.
And the other annoying thing is E doesn't mean error, it means exiting. So when it says E, it's finished. E doesn't mean error. It's very...
There it is. So now I should have profile files like that, and I can see at the end, this is the output file. If I say grep seconds in this, it took 24 seconds as expected, and that's not bad. I do have a full profile where I can see the time spent in various functions, but when I optimize it by opening it in ParaProf, and I had done this locally. And I had used paraprof --pack default.ppk to create this file, and used a default.ppk here, and I went over to paraprof. I could say file, create selective instrumentation file, and then these are the functions. Now notice that if I change this 10 microseconds per call to say 25 microseconds per call, this will update. Or if I say I don't care about 100,000 calls, even if it's 10,000 calls, I'm okay, then it will change the list. So in any case, I would save this file, select.tau, and then transfer it over to Archer. And here in the btmz directory, I had transferred it over. Here is the select.tau file, which says these functions, they are lightweight and should be excluded from instrumentation. And to do that, I said tau f77.sh, and in this list, it shows me how to set the tau options. So I can say export tau options equals single quote this, which is saying please use the selective instrumentation file called select.tau. And then I can go and do a make clean again, and then make suite with MPI f77 equals tau f77.sh. And here it is now using, if you look at this, the phases are, it runs opari. When you say launch f77 on a particular file like exact solution.f, it first parses it with opari, creates a pomp.f file for the exact solution.f, it turns it into exact solutions pomp.f, which is then parsed by the PDT parsers. And then they create a program database file which shows where the functions start and stop. And then it is passed to the tau instrumenter, this exactsolutions.pomp.pdb file. And then it takes the original POMP file and then creates the instrumented file. So you see the extension is going from exactsolution.f to exactsolution.pomp.inst.f, but here is the selective instrumentation file. The tau instrumenter also takes the selective instrumentation file to then create the instrumented.o file, the instrumented.f file, which is then sent to the FTN compiler and compiled into the original .o. And then we clean up all the other intermediate files like pomp.inst.f, pomp.pdb. If you didn't want to clean up, there is a tau option called opt keep files with the K and F uppercase. And then you can see what was there in the instrumented file. But otherwise, this tau f77.sh pretty much acts like a compiler. It creates .o files, and then you can generate the executable at the end, and all the intermediate files, the POMP files and instrumented files are deleted. Here is the file with the final instrumentation. This is the compact instrumented file. And now this is the older one from yesterday. Let me just delete that. I can say again q sub run.pbs, and I will be creating profile data from the optimized instrumentation, which will be more accurate. Now, what is interesting is that because we have a file that is very compact in its instrumentation, we can generate other types of trace data which will work with this. So we can look at other options that we saw before. Let's try first with the OTF files for Vampire. I'm not sure if Vampire is being demonstrated here in its own slot for this workshop, but I will show you a quick demo of how you can just use the same binary to generate trace files that can be loaded in the Vampire trace visualization tool, which comes from TU Dresden in Germany. And here is the data, and it's complete. And so I can say seconds star.o. And there you see the latest file 96 that we created. It took just 20.36 seconds. So it's very close to the time spent in the original file. If I say grep seconds in the bin directory star.o star. Yes, so this timing is very close to this timing. And even the first time that you run this, it's not too bad. It's 23 seconds. So even if you didn't optimize the instrumentation, you would get same results. Here I can say paraprof -- pack, and I say optimized.ppk. Okay. It says, oh, it already exists. Do you want to overwrite it? I say yes, and it overwrites it. And I can say transfer it over to the system there, remove the optimized.ppk, scp zorak, and then I can launch this paraprof visualizer locally and view the profile data. So here are the key functions and code regions that are of interest. And you can see here there are these three functions, and these are the do body loop body with xsolve.f and then ysolve, and then zsolve. The x, y, z, these are the three functions that are of interest. And then you can see exactly whether they were all behaving the same way on specific threads, or what is the shape of those. So you see for the 6 threads of execution, you can see that there is a pattern. There are 4 that take less time, and then there are 3 that take a lot more time in all those functions. So you can view that shape very consistently across all of them, and this makes it very easy to visualize and see what every thread is doing, and if there's a certain pattern that can be gleaned from looking at that. Here also you can see there are like 5, 5, 5, 5 in the top level timer. Now with this, you should be able to generate the optimized profile data, remove the old profiles, and let's try to generate trace files. Now trace files can be massive, but if I turn on the OTF2 tracing in Tau, I will be able to generate native OTF2 traces that are more compact. Compact because I have removed the instrumentation from all those functions that were lightweight and were called frequently. So if I say qsub run.pbs, let's see this job. Now it will perturb the application because it's writing out these large trace files, but I'm hoping that it will be small enough that we could actually attempt to take traces from all these 48 threads of execution and actually transfer it over to my laptop and launch the Vampire visualizer locally. Let's see if that works. That's an ambitious plan, but Vampire also comes with a Vampire server where you can keep the traces where they are on the server and just launch an analysis task right on Archer and connect to Archer through a visualizer client that runs on my local laptop, and then it uses sockets to communicate between the client and the server. And here it is. So let me say mkdir npb traces. Okay, and let us see traces that are generated here. Let me move trace star to npb traces. And tar czf npb traces.tgz npb traces. Or maybe I should have used J instead of Z, but so I have a license of Vampire locally on my laptop, and let us see how big these are. So that's not too bad. It's 101 megabytes of compact traces, and let me transfer that over. And copy it over to my laptop. And get rid of this. So I say open other local file, and within this I can look at a ppk directory that I have, and tw24 npv traces otf traces.otf, and there it is. I have Vampire, and if I want to change the colors, I can go to the Vampire preferences, click on this appearance, and say look at OpenMP, or look at one of these groups. That's odd, it's not letting me open the set random colors. Set random colors. Okay. If this is a function that I want to highlight, I could just say click here and go here and pick a different color, say magenta. And there, if I have another do XY and I say green, and then this one, I can pick a color, say orange. So now I have distinct colors for the do loop for the X, Y, and Z solve functions, and I can go into the application and see exactly in this big timeline display, I can see exactly which segment of the trace is interesting and zoom in all the way down and see what every thread, CPU thread is doing at any given instance. I can even, let me try and increase the size of this display. And here, you can see here are CPU threads 0, 1 through 5. And you can see all the thread ordering and see which function it is. This is ysolve.f. So it gives you a very interesting view of the X, Y, and Z solve kernels, or rather functions, as they are executing over a timeline view. And you can see the exact communication pattern here. If you see an individual timeline, rank 0 to rank 1 in MPI-COM world, tag and the start and stop times, and the and so on. So you can see exactly the communication that takes place between the threads and view the trace file. And as you saw, it was just 100 megabytes of the trace from all 48 cores, because we were able to use the optimized instrumentation in Tau and generate this. So is this workflow okay? Do you have any questions about this? And feel free to speak up. I just re-instrumented the code. I compiled it, I did this and ran it again and reduced the time. Were you able to do the same? Or maybe I should wait a few minutes and give you some time to try this.
So Samir, can you just recap what what are the optimizations which are performed to improve the?
So what I did is I launched the paraprof tool, and it identified the functions that were throttled
Okay.
automatically. And
Fine.
the
Okay.
parameters for throttling were that if the function takes less than 10 microseconds per call and gets called over 100,000 times, and these are just the defaults that Tau has, you can change those defaults by setting an environment variable. And so it identified a list of functions that it said that these functions should not be instrumented because they get called a lot and they take very little time. And so I created a filter file, a selective instrumentation file. I believe they may have done something similar in the ScoreP part as well. Has the ScoreP tutorial happened already?
Yeah, well, I missed it. I couldn't attend this morning, but I understand it was done. It was done. I just missed that step, so I wasn't paying. It's done. It's done automatically. So you have some internal thread. You take a first trace. You parse it. You feed that back in to optimize the next
Exactly.
run. Yeah, fine.
And it's just that paraprof does this automatically for you. You can also cut and paste it if you want and just create a file which says begin exclude list, end exclude list, and cut and paste all the names of those functions through the pprof tool too. Like you could say paraprof -- dump and then give the name of the default.ppk. So this pulls out all the profile files from there. You can say pprof-l and it will create a listing of all the functions. And you see these names, throttled. So you could say pprof-l grep throttled. And they are these functions. And then you could just cut and paste them in a selective instrumentation file that looks like, BTMZ. These files. So paraprof is just a fancy way of doing the same, but you can have a low-tech, cut and paste for the throttled functions and put them in this exclude list, and then again do the instrumentation by saying, export this tau options to say opt tau select file, which is the selective file, is this, and I had put it in the directory where the source code of BTMZ is located. So it picks up this selective instrumentation file every time it compiles the code, and then you do a make suite again, create the new executable, and then after you run that, you'll see that this is very close to the 19 seconds that the uninstrumented program took. So here is the optimized instrumentation, and because it is optimized, I can now generate trace files very easily, trace files that are compact yet reveal all the interesting details of the execution that I can then view in Vampire or other trace visualizers. I don't think this particular training workshop has Vampire session in it, but do you have a Vampire session in TW34?
We don't know because we don't have a license for Vampire on Archer.
Oh, you don't have? Yeah, I figured that.
There is no specifically session dedicated to Vampire. Christian covered a bit of it earlier on during the Scala.
Yes, and as you can see that all these tools have a great deal of interoperability between them, and that you can use one tool to instrument, the other tool to measure, and the third tool to analyze the data. And so that's what I'm doing, where I just said export tau trace format equals OTF2, and then it just out OTF2 traces that don't require to be merged or converted in any way. You can just bring them back to your system where Vampire license is installed and then view them. And you can see the full timeline from here to there, the full execution, and see exactly what each task was doing what each thread was doing. Were they shifted around while they were running the kernels, and see what everyone was doing at a very fine granularity. Here's the master timeline. There are other views that you can see, levels of nesting over here, and summary view. Message sizes, and you can say pie chart instead of the bar chart, and you can see exactly, if you want to open up a window, you can see it in detail and say, okay, there's this X solve, this is the Y solve, and then the Z solve. These three are the main contributors of time, and all these other functions, including all the do loops and all, that you can visualize. And you can do this for a given section of the timeline. So if you take this half, then this code is showing you this is the Z solve, Y solve, and X solve as the three main contributors. So Vampire is a very nice tool. It's considered by many to be the state of the art in trace visualization, and comes from our partners in TU Dresden. We highly recommend this. Maybe you should consider it installed for the Archer 2 system, where there may be interest in trace visualization. And here are the X, Y, and Z solve functions for the entire execution. So it immediately gives you a good overview. You can see the breakdown of OpenMP timings versus the others. Does anyone have any questions on the use of Vampire that I can answer? Okay, so let me move on and say, look at the case where you don't want to instrument the code at all. Okay, let's see how we can handle that case. Now I have in my home directory a workshop workshop.tgz. And if you just untar this in your Scratch file system, here is my the collab. I have some examples in say just plain C with MPI. Now, if I want to instrument such an application, let me just run.pbs, copy this over. So if I tar xf this particular location and then go to the workshop directory, there are several examples here that you can try. But here is a co-MD example, and I'll go to the source MPI. Now here, the only change I have made to the make file besides the compiler name as CC is that in the LD flags, here is the compiler name. There is a -G along with full optimization of O3. I have created a -dynamic argument because I want to use tau exec now to launch the application. And tau exec, as you may recall, uses the dynamic shared object of tau. It preloads that shared object, and then you can see the time spent in MPI and also enable event-based sampling to view the time in other code regions. So with this dynamic flag, I'm creating a dynamic executable. The default on PRACE is to create a static executable. So I can say make clean, make, and now here you see the O3 is being used, and then it creates a co-MD MPI with the dash dynamic flag. And this is a C program, and I go to the bin directory. I can, first of all, I should just make sure that I use the same reservation. This one is a run.pbs file that I have. So I'll close this short and then add this queue. Now you may notice that I have set tau exec with the GNU compiler tag EBS for event-based sampling, and then I just insert this tau exec before the executable and give it parameters such as use 4x4x1 grid of processors, and so I'm asking for 16, and I'm just using select equals 1. And then I'm saying, oh, the size of the problem is 80 by 80 by 80 for nx and y and z. And here I have a clean.sh file that cleans up, and I can just say q sub run.pbs. So the steps that I did in this case were I said tar xf uosmear packages workshop.tgz cd to the workshop directory. Then I did a cd co-md src mpi. I did a make clean and a make. Then I went to the bin directory, and then I said q sub. I could say clean.sh, and then I said q sub run.pbs. That's all. And you can look at the run.pbs file to see how I put just tau exec before an uninstrumented code. Now, what is important is that I did not modify this application using tau in any way. And here I can monitor. Okay. And there it is. It ends, and I create profile data. Okay. And let me pack this up and say comd mpi archer.ppk. And then launch the paraprof visualizer after this. So here is the profile. I can go to options, don't stack the bars together. They should be about 16 ranks. There are. And if I open up the thread statistics table by right-clicking over here, I can see that the total time spent in the application was 34.48 seconds, 34.42. It spent some time in the MPI finalize, send, receive, MPI calls like all reduce. But for most part, the application was doing work itself outside of MPI calls. And how do I know that? I can see that the exclusive time spent in the application was 33.91 seconds. Okay, 33.91 seconds on rank 0. And most of the ranks follow the same kind of pattern, except a few stragglers here. Now, with sampling in tau, we can explain 33.45 seconds. As you may recall, sampling is imprecise. We cannot have the same level of accuracy as the timers which are inserted like you did with Opari and PDT before. But this is close enough. 33.45 seconds can be explained by tau, 33.45 out of 33.91. So if we want to see where the application spent its time in the rest of the 33.45, I can expand this and see. Now you'll see that there are some functions that are right from the system, and you can click on this, then sort it, and it's color coded. It says this is red hot, this is a little orange thing here, and it's saying, look at this. Out of the 33.45 seconds, 28.2 came from this function called LJ force. And that's interesting. It says that there were several functions. One of them was LJ force. Then there was 0 real 3, advanced velocity, advanced position, sort atoms in cell, put atom in box. All of these are minor. This one is the heavy hitter, 28.2 seconds out of the 33.45 in the rest of the application outside MPI. But what is interesting is I didn't need to touch the binary in any way. I could just launch it with the tau exec tool, run.pbs. If I didn't use this tau exec, it would be the uninstrumented case. I just set tau exec -t GNU for the GNU configuration and event-based sampling, EBS. That's all. And I get the MPI data. I get the data for every function. And I can then expand this, open this key, and see exactly which lines in the code were important. It says 198 took 4.3 seconds, as did 202, 209, 193, 199. These are the precise lines that are taking so much time out of the overall 34%. I can even pick other columns, like if I say show columns and say inclusive percentage value, and I can get a percentage value here. I can move around the columns. So I can see that, well, 12.5% came from 202, 12.5 came from 198. And if I go to this line, this precise line, and see where exactly it was, I can go to the src MPI directory and say ljforce.c. And here, if I go to 199, set up the numbers, then here is the source code of LJ force. I'm not a molecular dynamics expert at all. Maybe some of you in the audience know the molecular dynamics code or what it's supposed to do better. But there is a LJ force function, and then at say line 199 or 198, these lines which are taking time, they are in this loop. 1, 2, 3, 4. 4 levels of nesting. Or is there another one? Yes, 5 levels of nesting of for loop. 1, 2, 3, 4, and 5. And then this line and this line are taking up significant portion of time, which is what the event-based sampling is able to show us with no changes to the binary. So here are the heavy hitters, and you can dive right down to the statement level and say, where is my application spending its time? Well, it's these functions and also some system functions like GI, memcopy, and then you can see exactly what the application is doing. In fact, if you want to see what functions are getting called inside system functions, or like the CRE MPI implementation of MPI send receive, you can see that it calls a function called CRE MPI memcopy SNB. I don't know what SNB stands for, but it's an informative name and it shows you exactly which library it comes from and what it's doing. So it opens up the layers of the runtime. You can dive deep into the code and see exact source line numbers. And all you had to do was say tau exec-ebs. Also have a source browser included in Paraprof. Fortunately, I have the source code of this workshop tarball over here, and it can jump right to that code. So I can just look at any execution and then just click on a show source file and launch the source browser. Okay. It also has this 3D visualizer, which will show me exactly which functions are taking how long. And here, this is the sample for LJ force. You can see that this is in line. (202). The next one over, 206. 199. So this is the line 199. I can look at the thread. And this is the, let me close this. So I can see exactly what that thread looked like by seeing the shape of all the samples and see this is where a lot of the individual thread samples are taking place. You can see the shape difference. Why is this different from that? There are 4 threads that take less time, and these are 16, right? So this is 12 and 4. And that's very interesting. There's something about the machine where there are 12 ranks that take a little longer, and then 4 take a little less time. Let's look at CPU cores are 12, and they are presumably 2 sockets on a particular node. So these are the 12, and then the second CPU, which gets just 4 of these ranks, it takes a little less time, right? So you can see that visually and immediately see that, okay, there were these 4 that were different and these that are doing something else. If you see the same thing, even a subtle change in the color here shows you the difference consistently across multiple ranks. Here I am moving the slider all the way over here. This is the summary LJ force function, and here is the rank 10, rank 11. It says 28 seconds in rank 11, and then if I go down to rank 12, it falls down to 26 seconds. So I can see that this summary, the main function for LJ force, looked like this across all the threads of execution. If you want to see individual threads, you can just as easily launch the thread view. Here is the application. And here, if you wanted to compare, you could say add thread to comparison, and then maybe add this thread to the comparison window. And there you can compare 2 nodes. You can say rank 10 versus rank 12. You can see that this took a little less time. and what was the effect for each of them, and send receive, there was a difference in the time. So it's just the mapping of the tasks to the CPUs that is causing this slight shift, which is visible here. I can look at any given node and say, show me the metadata for that node. It will show me the CRAE node name, node ID, and I'll be able to see that over here as well. So I can compare the node names and PMI rank and XYZ coordinates for that. And here is the 16 in a topology view. You see the XYZ, it shows you exactly which function is taking how much time. And here is the event. The color is a tau application. I can say change this to any function that I wish to visualize. Let's say I want to say a summary node. Okay, these are all the functions, summary nodes. I say this LJ force function should be color. And that's the color. And I can actually see in this topology view what that LJ force function looks like across all the cores. And here is the summary LJ force, which goes from 28 to 26, 26.3 to 28. And you can see where they were located physically on the system with the CRAE detailed information like that. So you can visualize large-scale executions, and Paraprof just natively picks up the topology view and maps it using the CRAE PMI. Any questions about what I've just showed? So if you would like, I can take some time for you to try some of these things yourself and try using Paraprof maybe locally or remotely, or just use pprof with text browser and examine the performance of this CoMD app or any other app that you may have. I'll stop speaking and just take questions at this time. And then after this, you can say pprof minus a minus m, pipe it to more after the job finishes, src mpi lj force.c, and go to the 199 or 198 lines. Is that okay? So let me know if I can answer any questions about this particular CoMD app, the NAS parallel benchmark app, or any other issues you may be having with your own applications. You can just use tau exec to launch your code, just as I did here. In this directory, there are configurations of tau, and you can see that there are some with Opari, some with pthread, some with just without threads. I use this without threads, and for GNU as well as Intel compilers. So you can just say tau exec -t intel PAPI and pthread, and then it will map this automatically to the one which matches best. You don't have to have all the options, or if it's not a MPI application, you'll have to say serial. But we have mostly MPI configurations. A.out. So app run -n whatever 16 tau exec like this. And if you want to generate EBS samples, you say EBS. So that's EBS. If you were using Intel, if you were using GNU, you could say GNU like that. This is for a multi-threaded application where you don't need to modify anything. The only thing you need to do is link your executable with the dash dynamic flag. And then you have a dynamic executable that can be used. Here you can see this is a dynamic executable because it's loading all these libraries. But there's no tau in this at all. I can say there is no tau symbol in this binary. It's a dynamic executable. I just launch it using something like this with tau exec, and it will generate all this data. Do you have any other questions about tau in general, or anything that we could not cover yesterday? I guess I'll just give everyone some chance to try their own codes or try this workshop example with C and try it with tau exec like I did with this. And ask me anything about this. David, does that sound okay?
There seems to have been a connection issue. I saw everyone being disconnected and reconnected.
Okay. Are you able to see my screen yet?
Not yet.
Here? Okay, here. Does that help?
Yeah, it's loading. Yeah, I can see it.
And it's the 3D graphics and everything works smoothly on the remote connection?
Yeah, quite well. Yeah.
Okay. The instructions I kept in the chat window, are they still there or they are gone?
So Samir, I lost your connection there for a bit. I don't know what happened.
Yes.
I think everybody got disconnected and reconnected because I too was dropped and reconnected, and I saw everyone else being disconnected and reconnected. So I don't know what happened. And by the way, yes, I mean all the code you wrote in the chat are still available.
They are available? Okay.
Yes,
they are
they
still.
are. They're linked to the session, not your connection. That's right. So that's good.
Okay. This is all I did there. Oh, and let's start up script to get tau in your path. Does anyone have any questions about what I presented? Do you have any general questions about tau or the examples, or if you have some other codes that you are working on, how I may assist you? Well, I realize it's getting late there in the UK. If you want to leave early, I'm okay with that too.
Did you see, Samir? Somebody wrote on the chat that they can't seem to have permission denied issues.
Please try it again. Yes, hopefully that should have fixed it. Here's a Fortran example, a simple one, matmult.f90. It does some matrix multiplication, and I can just compile it, make, and then launch it like this. Run.pbs has tau exec in it with the matmult, and at the end of this, it creates a profile file. I can pack it. And here is the output of matrix multiply in Fortran. And what is interesting is here is the summary view. It says line 34. This is the file that's taking most of the time. And if it says, well, I don't have matmult.f90 locally, do you want to add it? And I can say yes. And then I can add. And if I say there's a tau2 directory, and there's an examples folder. Matmult. I click OK and say close. Then it will bring up the source code, and it says this is the line where it's spending all this time in the application. So if I have thread statistics table, again, I can open it up, see the summary, and that's the line. That takes 0.15 seconds. Line number 34. That's the one. So you can easily find out what each rank is doing, and even if you want to see what's happening inside a particular function, here is what happens inside MPI receive on a PRACE system. So you can go and see that there is a MPID CH3I progress function, there's a poll active F boxes, cray MPI mem copy SNB, and see exactly what runtime functions are involved in the operation of MPI receive.
Yeah, there seems to still be a permission problem.
Permission problem, really?
Yeah, on the workshop.tgz.
No, still no permission. Okay. What if I, we have a.
Maybe you can simply copy it to the shared directory.
Yes, that's what I was thinking. Packages, workshop.tgz into the shared. And would you please try?
Okay, so for me it's working fine.
It is, okay. And so this example that I just showed you was workshop matmult make clean make q sub autocorrect. something like that. Okay, glad to see that it's okay. And a co-MD example as well. So I just wanted to give you a couple of different cases. The NAS parallel benchmark showed MPI with OpenMP. I had a C with MPI and now a Fortran with MPI as well. So I'm assuming that most of you have a, one of these three kind of cases with a combination of Fortran and MPI with C or C++, and having a tool that does not require any modifications to your binary and just operates on an executable level can be useful to get a quick overview of your application performance and even allow you to drill down to the source level and see on a statement by statement basis exactly where the application was spending its time. Should we just wait for people to try out some of these examples? Do you have any recommendations? David, Cedric?
Yeah, we could still wait a few minutes.
A few minutes, yes.
And anyway, we're almost finished. We're almost reaching the time for ending today's session. So if that's okay with you, we can wait five minutes to see if there was someone doing something.
Please try this with the workshop examples. We are also creating containers which have Tau pre-installed in them with all the MPI and other dependencies and packages. This is part of the E4S project that I'm involved with. And e4s.io is the web page where you can download these containers, Docker containers, Singularity containers, and they are available for x86-64, PPC-64LE, and even ARM64. So if there is interest, you can go directly to the GitHub or Docker site and download the particular image. We also support AMD ROCm and CUDA in these images and have pre-installed Python packages like TensorFlow, PyTorch, and so you can use them directly on systems. Here is an example of a Singularity image. I'll just go to a system which has AMD GPUs on it. And if I say Singularity exec, this particular image that I can easily download from my e4s.io webpage, like the Singularity x86-64 download, then I can just say execute this image and give me a bash shell with startup with etc bash rc like this. And I am now in Singularity. And if I say which SPAC, I have SPAC package manager and 50 different ECP software technology products like SuperLU, SuperLU Dist, Strumpack, Rylinos, all pre-installed in that same image along with Tau like this, and has support for Python and packages that use Python. For example, if you wanted to use TensorFlow with the AMD GPU, first of all, you can say ROCm info, which should be in your path, and it will show you that it's a Xeon system with an AMD GPU, which is a Vega 20 AMD with a GFX 906, which is a MI50 card, and they are actually two GPUs, Vega 20s. So normally a user will find it very hard to install AI ML packages, but here everything is pre-installed. So you could say import TensorFlow, for example, and it will just load up a TensorFlow that works on the AMD GPUs. And if you wanted to check that, you could say TensorFlow test is GPU available. And sure enough, it says true, it is available, and that there is a Vega 20 device 0 with a 16 GB RAM, and then Vega 20 device 1 physical GPU. So you can use this, you can use Tau along with this. If I say dev shm, let me go to say tests, and here's a HIP or OpenCL, add 4. If I say make, then which HCC, the HCC compiler, is pre-installed in your path because it's all in the Singularity container, which accesses the GPU. And if you wanted to run this stream GPU HIP example, GPU stream HIP, it's running this and it shows you. Now, if you wanted to use this with Tau, you can again say Tau exec. This is not MPI, so it's serial, and then rock profiler, and then enable the ROCm. This enable ROCm will allow you to measure the time with the kernels executing on the GPU thread. So this is thread 1, and there's a kernel called add, there's a kernel called triad, copy, and multiply. You can see exactly what each GPU is doing. There's another case. It's called GPU burn, and it just runs some tight loop on the GPU. And if you want to measure the timings on that, we have the same thing with CUDA as well. You could say module avail CUDA, and then you have CUDA support built into the whole CUDA is part of this Singularity image. So you can say build GPU burn HIP, and it's running this on 2 GPUs now. You can see the temperature rising from these burn threads. In the US, AMD GPUs are becoming more and more relevant for the Frontier and El Capitan exascale systems. So we have added support for that. And I can again say build GPU burn. It's running the code. and I'll get profile files where you can see thread 1 for GPU 0 and thread 2, and you can see how many times the HIP SGM kernel was launched on each of those GPUs, and get detailed performance data, and even use event-based sampling if you wanted to see what's happening in the rest of the code. And here are pthread calls and all. We have support for OpenCL as well. Here is a simple convolution. I can say run.sh, and it generates profile files. You can see all the OpenCL calls. You can see bytes transferred between host and device, the other thread calls, and also on this thread number 5, you can see individual kernels running from OpenCL, and read buffer, write buffer, simple variable convolution passes. So we have one single image which has all of these tools pre-installed in it in Docker or Singularity images, and we have several. We have a virtual box image with all of our tools pre-installed as well, or we have base images that you can build upon to create your own custom Docker images. So we're just doing this to help package the software a little better. I hope you find this useful. Please check out the v4.io webpage and let us know. I don't know if you plan to, David, do you have plans to deploy Singularity on your new Archer 2 system?
Yes, so that's one of the big differences, hopefully, between Archer 2 and Archer. Archer was very difficult to have containers on. I don't know quite why kernel, I don't know, but Archer 2, I understand, has been built with that in mind. So that will be something we don't have access to the system yet, but that is something we're very keen on doing. It'll be one of the early courses we run, containers on containers on Archer 2. Yeah.
Would you like us to present the E4S containers with all of these tools in a training workshop on Archer 2?
We need to, because the time scales are very, very unclear at the moment, but it's something we'll need to, so the initial, there's something we'll need to think about. Yeah, we need to think about what tools we can offer. But I think the ability to deploy containers will make running training courses much easier, because we'll just be able to give this, you say, a users a shrink-wrapped environment, and off you go, even on the production system. But we have no idea how that's going to work. So that'll be quite a long way down the line, I think. But it's something I'll keep in mind.
Well, if you would like us to test our tools on that, please let me know, and I'll be happy to be one of the early testers.
Very, very keen to get people on early to try these things out. So yeah, when it's open and stable, we're very keen to get the full VI-HPS suite up and running on Archer 2. Will be quite important.
Great. Well, I hope you found the workshop useful, and please let us know how we can assist you further going forward.
Yeah, thanks. And thanks. The technology seemed to work out fine. So if there's nothing more from Samir, we're starting again the same schedule at 9 tomorrow, and it's going to be the Macaque tools. I think is that how I pronounce it? In the morning. Macau, sorry, Macau. And then in the afternoon, it's going to be the ARM. Now, sorry, Macau. I misread that. I don't think that. I think it's Timothy Duthie is giving the ARM talk. He's not on the line. He's been having some problems connecting to Archer. I'm offered to help him, but he hasn't got back to me. But we have some time to sort that out. If not, he can demo it on any platform, but it would just be nice if he was able to do on Archer. So thanks everyone, and I'll stop the recording now, and we'll